So Chapter 11 has to do with substitution and elimination reactions, and these are a very important topic, definitely one that we are expected to cover in first year organic chemistry. For both of these reactions, we have a leaving group, a lot of times represented by X. But there's two different types of products that result. From a substitution, you substitute X with another group, Z, a nucleophile that comes in and attacks this electrophilic carbon that has X on it, and Z results in being on that carbon. So it substitutes X. And for an elimination, this nucleophile, instead of attacking a carbon, attacks a proton. And so we have a carbon that has the leaving group, another carbon that has a proton on it, and that Z, many times negatively charged, grabs that proton, and then we have the leaving group leave, and we end up with an alkene. So it's the opposite of an addition. In an addition, an alkene gets a proton and some other kind of group, an X group, added to it, and in an elimination, the X and the proton are eliminated and they leave, and there is a pi bond that's created. A lot of times we can get mixtures of products from these elimination reactions. Let's see if we could come up with some products, both substitution and elimination, for these compounds that have leaving groups over here, the starting compound. Remember that for substitution, the Z group ends up replacing the X group where the X group was. So these are a little bit easier to draw, I think, especially since we are not yet concerning ourselves with any chirality, any stereochemistry here. For the elimination products, we have to remember that the carbon that has the leaving group is going to lose the leaving group, and then there's a neighbor that is going to lose a hydrogen. Here we have two possible neighbors that could lose a hydrogen. So we have two possible products that could form. If we pick on this top carbon here to lose a hydrogen, that's where the pi bond is going to form. And if we pick on this lower carbon to lose a hydrogen, the alkene will form in the other location. For this one over here, the carbon that has an X only has one neighbor that has a hydrogen. So there's only one possible product, only one location for that alkene. And here we have a similar situation. We have a carbon that has the leaving group. This neighbor does not have a hydrogen on it. It has other carbons on it, so we cannot pick on that neighbor at all. We're going to have to pick on this neighbor. So we only have the one possible product. And we have a similar situation here. This carbon cannot be picked on. It does not have a hydrogen, so we're going to have to pick on that neighbor. So here are the elimination products. There are two kinds of substitution reactions called SN2 and SN1. The 2 and the 1 refer to what is participating in that rate limiting step, whether just one compound with the leaving group is having the leaving group fall off by itself, or whether two compounds are coming together, the one with the leaving group is being attacked by the nucleophile, and they're both coming together in that transition state. So for SN2, we have two things coming together. We have both the nucleophile and the electrophile, or the alkyl halide, in that rate limiting step. And so this is a one-step reaction. So it does not, the 2 does not mean that there's 2 steps, it's a one-step reaction. All right, so I'm going to try to draw this alkyl halide kind of on its side. I'm going to draw the long, so I'm going to draw this on its side. I'm going to try to draw this stereocenter. The propyl group is pointing down, and then I'm going to have the X out to one side here, the incoming nucleophile off to the other side. So when the X is pointed in that direction, like if we sort of tilted this up and had the X point in this direction, then this hydrogen is back away from us. And this methyl group, the methyl group that's over here, is kind of coming out towards us. So if we just sort of lifted this up and pulled this towards ourselves, the X would be on one side over here. Then as this X leaves from one side, the nucleophile is coming in from the other side. So we have a partly negative nucleophile, a partly negative X group coming in. When the X group leaves, it takes the electrons with it, so the X group now has a negative charge, and the nucleophile that came in does not. And you'll notice that there was an inversion of the stereochemistry here. So before, the starting material had the H pointing back. Now the H is pointing forward. It's a wedge. So it's gone from being a dash to being a wedge. So this is an inverted stereocenter that happens. And remember, transition states tend to look kind of weird. So instead of having a full negative charge and a full bond, we have partially formed bonds to the X and to the B, and we have partial negative charges on both of those. So that's one of the reasons why the transition state is very unstable, because the bonds aren't completely formed, they're not completely broken, so it's just sort of in this strange high energy transition state. So let's draw some more substitutions. And remember that if there is a stereocenter and it's an SN2 reaction, the nucleophile is going to come in from the opposite side. So here we have the bromine sticking up. This oxygen is our nucleophile. Those are the electrons that are going to attack. They're going to attack from the back. So the bromide had been a wedge. Now we have the oxygen as a dash. The other product is bromide ion. We usually are not too concerned with the non-organic piece, but that is what comes off of there. In a similar way, when the iodine is pointed back, the CN group that attacks is going to be forward. It's going to have a wedge rather than a dash. This last one does not have a stereocenter. So at first, if this attacks, we would have the nitrogen still having a positive charge, because we have something neutral and something neutral coming together, so we need something with a positive and something with a negative. And then if we raise the pH of that, we can get this to be a neutral nitrogen. We could show the loss of a proton over here. So this is generally not a very useful reaction, because sometimes it's hard to prevent the nitrogen from attacking another alkyl halide and making another bond here. So you sometimes tend to get a mixture of products, but just to practice substitution, it's an okay example, I guess. So just to go over the kinetics of this, since both the alkyl halide and the nucleophile are part of that rate limiting step, then when you double the concentration of either one of those, the rate will double. If you doubled the concentration of both, then the rate would quadruple. So it would be 4 times as high, because you're doubling the concentration and you're doubling the alkyl halide. So by the end of the chapter, we'll try to be able to decide what type of reaction is taking place, whether an SN2 reaction is taking place or one of the other reaction types is taking place. And so we'll need to be looking at the substrate, the nucleophile, the leaving group, solvent, temperature, different conditions that we can have in our reaction. So let's take a look at the substrate. Since for an SN2 reaction, we have to have a nucleophile coming in from the back side of a leaving group and attacking it, if there's too much other stuff in the way, if it's too hindered, it's not going to happen very easily. So we have the slow end of the chart is over here over to the left, the fast end is over to the right. So if we take this primary alkyl halide that unfortunately has some hindrance not too far away as our rate equal to 1, if we set that equal to 1, then the tertiary would be a lot slower. Secondary would be a little bit faster, actually, because we don't have all this bulk in the way. Primary without all the bulk in the way would be a lot faster, 40,000 times as fast. And then methyl would be 2 million times as fast. So the bulk that's around the alkyl halide that's blocking a nucleophile from being able to come in and push out the leaving group can really have an effect on the rate. Even though vinyl and aryl halides might not be as hindered, they do not undergo substitution reactions. They don't undergo either SN2 or SN1 that we'll learn about in a bit, and they also don't undergo E1 reactions. So even though these look like alkyl halides, vinyl and aryl halides are a special type of alkyl halide, and they don't undergo these reactions in the same way. We did learn in Chapter 9 that you can take a vinyl halide and remove a proton from the neighbor and let the leaving group leave. If you have very, very strong base, very, very harsh conditions, you can get that to happen. So you need like a negatively charged nitrogen. This is the one we were using in Chapter 9, and we can remove this hydrogen and kick off the bromine and make an alkyne. And if you have an alkane with 2 bromines on it, you can do it twice. You can get to the alkyl halide and then do another elimination and get to the alkyne. So this is an E2 reaction. We learned about it before. We learned that it was called E2. So back to our SN2 reactions. We need a pretty good nucleophile to come in and kick off that leaving group, and nucleophilicity tends to be correlated with how basic something is. So if something is a base, it really wants to attack a proton, which is an electrophile, and then a carbon with a leaving group is also an electrophile. So something that is better at attacking one kind of electrophile, it makes sense that it's also better at attacking a different kind of electrophile. So things that are stronger bases tend to be better nucleophiles. A lot of times the strongest, best nucleophiles will have a negative charge on them. So as we mentioned before, stronger bases are usually better nucleophiles. This is especially true if you have an aprotic solvent, something that is not capable of having protons associate with the nucleophile, which is also a base. Remember, a lot of these nucleophiles tend to be bases as well, and so if there are protons around, those will get attracted to the base and they will make less available base for attacking other electrophiles, which is what you might want in a substitution reaction. So here I've just drawn on the side, bases and nucleophiles tend to be the similar types of compounds. When something's acting as a base, it's using its electron density, let's put this as negative, to attack a proton, a positively charged hydrogen. This is something that is more useful when you're doing an elimination. So an E2 mechanism, you want something to act as a base. If you want something to act more as a nucleophile and attack a carbon that is electrophilic, maybe has a partial positive charge, then that would be giving you an SN2 mechanism. So for SN2, we want something to act more like a nucleophile, and we don't want it to attack a proton. So if we want that substitution, then it's generally better to have an aprotic solvent where there's no protons around to distract the nucleophile from what we want it to do. So protic solvents tend to distract nucleophiles and slow down SN2 reactions in general. This is especially true of small atoms like oxygen and fluorine. These are pretty good nucleophiles. They're with strong bases, and so they're pretty stronger bases. They're better nucleophiles in the aprotic solvents. When you have protons around, they tend to get distracted. So you'll notice that the O minus, instead of being the best one, is now only the 4th best one. And the fluorine, instead of being better than chlorine and bromine, is now worse than chlorine or bromine. So it's sort of changing the order of the halogens. So the smaller the halogen, the worse it is when there are protons around to distract it from trying to do a substitution. So I've added a few more nucleophiles in this second list here, or this last list. So the cyanide ion and this amine are better bases than these halogens, so they would be sort of in the middle here, like right before the fluorine here. So in addition to steric hindrance on the alkyl halide, remember the tertiary alkyl halides do not do SN2 reactions very well because there's too much branching, there's too much stuff blocking the way for the nucleophile to get in. If the nucleophile itself, like this alkoxide over here, this negatively charged oxygen, is a lot more hindered, this is called tert butoxide versus ethoxide, which has it's the anion of ethanol. It's the conjugate base of ethanol is ethoxide. The conjugate base of tert butanol is tert butoxide. So the alcohol itself, tert butanol, has a pKa of 18 versus ethanol with 16. That makes ethanol a slightly stronger acid. That makes ethoxide a slightly weaker base. So ethoxide is a weaker base, and tert butoxide is a stronger base. We can tell that because of the pKa's of the conjugate acids. But because the tert butoxide is more hindered, it is not as good at being a nucleophile. It is not as good at attacking a leaving group and getting in there and being able to attach to a carbon because of all this bulkiness that's in the way. All right, another consideration is the leaving group. So we can have leaving groups that are more willing to leave and are better leaving groups versus leaving groups that are less willing to leave, and so they're not great leaving groups. So you need something that is happy with the negative charge that it is taking with it. So this is something similar to being willing to lose a proton and get a negative charge, being willing to break a carbon bond and get a negative charge correlates with that. So something that is a weaker base, so something that's happy with a negative charge, is going to be a better leaving group. Something that is a stronger base that's not as happy with a negative charge is going to be a poorer leaving group. So just looking at the halogens and comparing them to each other, so looking at the conjugate acids, HI is the strongest acid, even though all of these are very strong. They have pKa's lower than 0. HI, HBr, HCl are all very strong acids, completely dissociated in water. And so we usually don't think of comparing them to each other, but if we did compare them to each other, HI is actually even stronger than HCl. And then HF, even though it is very corrosive and you need to be very careful with it, it's technically not a completely dissociated in water, and so it's not classified as a strong acid compared to these others. Fluoride is the worst leaving group because it is a stronger base than any of the other halogens. Iodide is the best leaving group because it's the weakest base of all the halogens. However, all of the halogens are pretty good leaving groups. None of the halides are very strong bases. All of them are fairly strong acids. Even hydrofluoric acid is pretty strong compared to some of these other ones with pKa's not 3 but like 15 over here. All right, I should probably fix this one over here because the conjugate acid of hydroxide is water, which has a pKa we know of 14, not 15, but still that is not a very strong acid, and so hydroxide is a pretty strong base, making it a very poor leaving group. So if we want to have this OH leave, it's definitely a lot easier to do if you put a proton on this. So if you do this in acid, now you have the leaving group, instead of being hydroxide, the leaving group is water. And the pKa of the conjugate acid of water, which is H3O plus, the pKa of that conjugate acid is very strong. It's below 0, minus 1.7. And so this is a much better leaving group because it's a very weak base compared to hydroxide. So remember, strong bases are very bad leaving groups. Something else that you can do to an alcohol besides put a proton on it is convert it into a sulfonate ester. That would make this the leaving group, the sulfate leaving group, and then the conjugate acid of that is something that Structurally, it's very similar to sulfuric acid, a strong acid. It's just that it has an R group on it instead of another OH group. And so this is pretty strong acid. The negative charge is delocalized over all three of these oxygens, making it very stable. The pKa of the acid is -6, so this is a very strong acid. This is a very, very weak base, and that makes it a better leaving group. So now we are correct in saying that the pKa of an alcohol is 15. It's slightly less acidic than water. So we have a stronger base even than hydroxide, this alkoxide ion, because the acid is a little bit weaker. We have a very strong base. This makes a very bad leaving group. So to make this a good leaving group, we can't convert this into a sulfonate ester, but we can do what we did in that first column, and we can give it a proton. So now it is a better leaving group because it's a very weak base. The conjugate acid of that weak base would be a protonated alcohol, which is very acidic. So very strong acid makes the conjugate base a very weak base, so that is a much better leaving group than this alkoxide ion, which is a stronger base. So these amines are even more difficult. Look at how the pKa of a regular neutral amine like this is extremely high. This is not a very strong acid. Amines usually we think of as bases. We have this lone pair that wants to take on a proton, let alone losing a proton. So it's very difficult to get this to lose a proton. This is a very, very strong base. You're not going to be able to get this to be a leaving group. We're not going to learn about amines being leaving groups for quite a number of chapters, but when we do look at them, we are going to have this ammonium ion, so either an R or an H has to be added to this to be able to get this to leave. So now we have the conjugate acid of this being a stronger acid. This is a protonated amine, an ammonium ion, and the pKa of that is around 10, and so much stronger acid than this one with a pKa of 40. So we have a weaker base. Even though amines are slightly basic, they're not as basic as the negatively charged nitrogen, and so this would be a better leaving group than the other nitrogen. It's still not fantastic because, again, 10 is not as great as these other super strong acids. It's not the best leaving group. So remember, we're talking about the leaving group being a base, and we know that it's a weak base and a good leaving group if the conjugate acid of that base is a stronger acid. So here we have a protonated sulfur, pretty strong acid, -6 is the pKa, and so we know that this neutral sulfur is a very weak base. It does not really want a proton, so it's a pretty weak base, and so that is a better leaving group than sulfur that has not been protonated, is not positively charged, is not going to leave as easily because it is a little bit of a stronger base than the neutral sulfur. A sulfur with a negative charge is a stronger base, so it doesn't leave as easily as a sulfur with no charge. So the substitution reactions we were just talking about are called SN2 reactions. The SN1 reaction is a nice complement to that. So we talked about how tertiary alkyl halides are not very good candidates for SN2 reactions. They react very slowly because the nucleophile cannot push off the leaving group. For an SN1 reaction, we have a leaving group leaving on its own, and then the cation forms. And so tertiary is actually better than primary or secondary for that. So tertiary halides tend to do SN1 reactions when they do substitutions. Then for the SN1 reaction, in contrast to the SN2, we don't need a really great nucleophile because the cation, the carbocation that forms, is very easy to get attacked even by a weak nucleophile. So this is also sort of complementary. You need a good nucleophile for the SN2. You need a primary or secondary halide for SN2. For SN1, you kind of need the opposite. You need a tertiary alkyl halide or another kind of stabilized cation. Allylic or benzylic halide will form a stabilized cation. And you don't need a good nucleophile. You can have a weak nucleophile. So let's take a look at this reaction diagram, which is different from the SN2 reaction diagram. This diagram has 2 steps, whereas the SN2 had only 1 step. So it might seem weird that the SN1 has 2 steps where the SN2 has 1 step, but that is because the thing that is taking part in this rate limiting step is the alkyl halide having the leaving group leave on its own. So I've drawn a secondary allylic alkyl halide because then we will form this secondary allylic cation, which is fairly stable. So it's easier for this leaving group to leave on its own. Okay, so this is hard to represent in 3 dimensions, but I'm trying to draw these all in a plane. We're going to make a flat carbocation. This carbocation is flat, so I have the 3-carbon chain kind of pointed straight down. This H is supposed to be going back away from us, and the methyl group is supposed to be coming towards us. And then this X group is leaving off to the left. We have a partial negative charge on that because when it leaves it's going to be negative. We have a partial positive charge on the carbon that is being left behind because that is going to be positive when those electrons finish leaving. So we have this flat carbocation. So this next transition state shows the nucleophile coming in a second step. So this cation is flat. I have the nucleophile coming in from the opposite end, so that would create this inverted stereocenter. However, since the carbocation is flat, we could also have it come in from the same side that the leaving group just left from, and so that would give the stereocenter looking the same. So the X had been a wedge, the nucleophile coming in could be a wedge, or it could be a dash. So you get a mixture of stereochemistry at that new site, because this intermediate that forms is a flat cation, and so the nucleophile can attack from either side. We commented before that the solvent can affect an SN2 reaction. It can also affect an SN1 reaction. Since our unstable intermediate is this charged carbocation, ions dissolve better in hydrogen bonding solvents that are protic. So this will be better for the SN1, the polar protic solvent, because it helps to stabilize that charge. Whereas we said before that the aprotic solvent interferes less with the nucleophile, and for an SN2 that is more important for the nucleophile to be a good nucleophile and be able to push out that leaving group. For SN1, the nucleophile does not have to be fantastic because the leaving group leaves on its own. It does not get kicked out by the nucleophile. And so for it to leave on its own, the protic solvent is going to stabilize the cation that's left. So polar protic solvents tend to be better for SN1 reactions, whereas we had learned that polar aprotic is better for SN2 reactions. Since only the alkyl halide is participating in that rate limiting step, then only changing the concentration of the alkyl halide will change the rate. So the alkyl halide is needed for that rate limiting step. So if you increase the concentration, that is going to increase the rate. If you double the concentration, it will double the rate. The nucleophile does not take part in that rate limiting step, so the rate will not change if you change the concentration of the nucleophile. And then if you doubled the concentration of both, the alkyl halide is the only one that would have an effect. The nucleophile would not have any effect. So it would only double, it won't quadruple like it did for the SN2. So let's look at what these products would be. We'll have the final product over here. So the final product is going to have that iodide substituted with that methoxy group. So on the way here, what's happening, we'll put a little intermediate here in parentheses. First we have the iodide leaving, and we have this carbocation left behind. And then the methanol, the oxygen of the methanol is the one that has the lone pair. The carbon of the methanol does not have a lone pair. So the oxygen of the methanol is going to get attracted to that cation. The oxygen still has that proton attached though, so we have something temporarily that has a positive charge. And then if this proton leaves and falls off, then we can eventually have just a regular ether. I'll draw the proton over here on the side. It has fallen off. So that is our final product, this methyl ether. The iodide is also hanging around here as well. I'll just draw it off to the side here. This one, the final substitution product, is going to be this benzyl chloride instead of the benzyl bromide. Along the way, what we get is this stabilized cation. We also have some bromide hanging around. So here the bromide has fallen off on its own, this SN1 reaction. We also have some chloride, so this chloride will be attracted to the positive charge of the benzylic cation. So chloride, remember, is not as good a leaving group, so it tends to favor the chloride over the bromide if you have a mixture of both chloride and bromide ions around. So here we have a question over which alkyl halide will undergo SN1 more easily. Remember, we have to have the leaving group leave as the first step, the rate limiting step in this reaction. So since this one leaves to form a secondary cation, whereas this one would leave to form a tertiary cation, this tertiary cation is more stable, and so that would be a more favorable situation. So this tertiary chloride is going to be a better candidate for SN1. For this second example, we have an allylic halide, and so this is going to form an allylic cation when the halide leaves. It looks not so great to begin with because it looks like a primary cation, but remember there's delocalization, and so that stabilizes even a primary cation fairly significantly. So we have this as the carbon piece no matter which halogen leaves. So that's not the difference in the pair. The pair is different based on iodide leaving versus chloride leaving, and so since iodide is happier with that negative charge, it's a better leaving group. It's a weaker base than chloride is, and so that would leave more easily and form this cation. So that would be a better SN1 candidate. So we do have substitution and elimination reactions taking place in a biological system. Those molecules tend to be a little bit more complex, so I haven't written as many of them down in the note packet, but go ahead and take a look in your textbook and just get a sense that these types of reactions are not just in the lab, they also take place in your cells, in your body. There are two different types of elimination reactions. Similar to the substitution reactions, we have one called E2, where two things are coming together in a one-step reaction. Let me draw what the transition state looks like. The base is pulling off the proton at the same time that the leaving group is leaving. So here is how that looks. The base is no longer completely negative, it's partially negative because it is starting to use its electrons to form that bond to the hydrogen, the proton that it's pulling off. The bond from hydrogen to carbon is breaking and starting to form this pi bond, a double bond between the carbons, and the X group is starting to leave. So since all of these things are starting to happen and haven't quite happened yet, that's what makes it so high energy, this transition state. And then the product that results from that is the double bond between the carbons. The base now has the proton, it's the conjugate acid, and the leaving group has left and also has a negative charge. So you start with a negative charge and with a negative charge so that that balances out. Also notice that this transition state, I've drawn that the base is pulling the hydrogen off on the opposite side of the pi bond, the forming pi bond, then the leaving group is leaving from. This geometry is needed for an E2 reaction. We'll talk about that a little bit more, but it's this called an anti-periplanar geometry that is happening. Similar to how the SN2 had a geometry, had an inversion of stereocenter, this E2 reaction also has a stereochemistry and a shape, a geometry associated with it. Whenever possible, the alkene product that's formed is the more substituted or the more stable alkene product. There's a couple of exceptions here and some examples to try to illustrate these exceptions. So sometimes the more stable alkene is not the more substituted alkene. The main time this happens is when the alkene is conjugated. So the more stable alkene might be conjugated, and it might not be the most substituted possibility. Some other exceptions include with fluoride or other poor leaving groups. We'll see some others in a later chapter, but for now, fluoride, the less substituted one forms because there is more negative charge on the carbon during the transition state, and for carbon, the less substituted carbon makes a better anion, just like the more substituted carbon makes a better cation. For negative charges, you don't want as many alkyl groups on the carbon. And finally, if the halide and the base are very sterically hindered, the base might not be able to get to a proton that is on a more substituted carbon. So let's look at these examples. We have, again, for an elimination, the carbon that loses a leaving group. There are two possible neighbor choices that we could make. If we choose this more substituted carbon to lose that proton, we would get the more substituted product, which follows Zaitsev rule or Zaitsev rule. So we would get the Zaitsev product. We might want to draw this with a squiggly line to show that we could get a little bit of the Z, a little bit of the E product forming. But these are both the more substituted, the disubstituted. The anti-Zaitsev product would be the other neighbor getting picked on. So this is a monosubstituted alkene, and that is less substituted. So that is not the Zaitsev or Zaitsev product. And this is also observed for Hofmann elimination. So this is sometimes called the Hofmann product, which we'll learn about later in the course. But the more substituted product would be the Zaitsev product, and in this case that would be favored. There's nothing in the exceptions column that applies to this case, so we would get the more substituted product here, and probably the even more stable of the two would be the E configuration. So this one would be probably the major product, maybe a little bit of the Z product, and this anti-Zaitsev would be a very minor contributor if we found any at all. So looking at this second one, B, we have the bromine on this carbon. That's the one that's going to leave the that's the one that's going to lose the bromine. And then we have two different neighbors to pick on. If we pick on the more substituted neighbor, we will get the more substituted product. That is the Zaitsev product. If we pick on the other neighbor, we get this less substituted, disubstituted product. I've drawn both the E and the Z forms. But these less substituted products have the alkene conjugated with the benzene ring, so that makes them more stable. Let's circle the most stable product as the major product, and this would be the anti-Zaitsev, or an exception to the Zaitsev rule, because it's a less substituted product, but it is the most stable product. So for this one, we have the fluorine leaving, the fluoride leaving group, and so we do have two possible neighbors. For this one, picking on the less substituted neighbor is a little bit better because it puts negative charge onto a less substituted carbon. So let's draw the two types of products. I'm going to go ahead and draw this with a wavy line to show that I mean to represent both the E and the Z for the more substituted product. Also, I'm going to give myself some more room here by erasing the benzene ring and drawing pH for phenyl. Phenyl group is another name for a benzene ring. So now I can fit this product a little bit better. This one is neither E nor Z, so there's only one possibility here for the monosubstituted product. And then for the poor fluoride leaving group, that would be the one that forms. All right, and so here we have the last example with the bromide on this carbon. We have 3 possible neighbors, actually. We have this one, and this one. These 2 over here on the left would give the same product. They're kind of both the same, so if you made the alkene there or there, it would be the same thing because this other bond rotates. Picking on the more substituted carbon gives this more substituted Zaitsev product. Picking on the less substituted carbon gives this product. Again, if you drew this up and down, it would be the same as drawing it to the side, just that the bond has rotated. So there's just that one possibility. And since the both the alkyl halide and the base are so bulky, you'll probably get a significant amount of the anti-Zaitsev product in this case because of all the hindrance. So this particular problem was trying to illustrate a lot of these exceptions, and so we're getting a lot of the anti-Zaitsev product, but a lot of times for normal cases the Zaitsev product is more stable, and so that is the one that forms. So for this next problem, we're trying to think about which alkyl halide would react in an E2 reaction more easily, more quickly. And the things we're looking for here are the alkyl halide that would be able to form a more stable product, because that will help lower the energy of the transition state as well. Also, if there's a difference in leaving group, having a better leaving group would help it be more reactive. Let's see what we have here in our examples. So here we have 2 examples, a primary halide and a secondary halide. This primary halide can only form a monosubstituted alkene, whereas this one is able to form a disubstituted alkene. So since that is a more stable product, that's going to be more reactive in the E2 elimination. Here we have 2 alkyl halides that would form the same types of products, the same mixtures of products, and so the difference here is the leaving group, and iodine is a better leaving group than bromine. Iodide is better than bromide. Here, if we look at this alkyl halide, both of them are secondary, but this first one would be able to form a conjugated diene. This one over here would form the isolated diene. There's this sp3 in the middle. They're not conjugated. The electrons can't delocalize, and so this would be a more stable product. It would be easier to do an elimination reaction on this one. This one's almost a little bit of a trick question. We have a compound that is not able to do an elimination at all over here. So we have a carbon that has the chloride on it. The next carbon over does not have a proton that the base can take off and make the alkene at all. If you tried to make an alkene, you'd probably end up either mixing up where the carbon skeleton is attached or drawing a carbon with 5 bonds. So either way, that is not going to happen. This one over here does have a neighbor that can lose a proton. So you are able to get this product. It's not a very substitute product, but definitely better than no product possible. Here, looking at the products that are possible, we have a disubstituted versus a trisubstituted. This one is more stable. So the better product means this halide will react more quickly. And we have a similar situation here. We have a more substituted product for this second bromide versus this first bromide. I already drew the product up here. So we'll go ahead and choose the second halide as the more reactive. So here we are also looking at the stereochemistry of the product, whether the E or Z isomer forms. We mentioned that, of course, the more stable one is going to form more easily. So this one is pretty symmetrical as far as regiochemistry. We're going to get 2-pentene. We could get the E or the Z. The E is going to be more favored. Again, the second one is fairly symmetrical as far as regiochemistry goes to cut down on the number of possible products we're drawing. We have an E column and a Z column. The E column has these 2 larger groups on opposite sides, giving it more room. So that one is going to form more easily. This last one only has one possible product. When you draw it, you see that both of these are methyl groups. So if you switch them you get the same thing. So since I drew it in a column that makes it look like it's E, I wanted to make sure that we knew that this is not E, but it is the only product that could form. So another stereochemical consideration that we mentioned before is the anti-elimination of the E2 reaction. So we have to have the base coming in from one side of the new forming pi bond and the leaving group leaving from the other side. Here we try to show this both as a stick drawing and as a Newman projection. And you'll notice that the R group, R1, is on the same side as the methyl group, whereas R2 is on the same side as a hydrogen when it's in this anti position, having the base come in here and the leaving group leave from the opposite side. So when you form the alkene product, you have the one where the R1 group is on the same side as the methyl and the R2 is the same side, on the same side as the hydrogen. In order to form this other isomer, like if this is the Z isomer, this might be the E isomer. In order to form this one, we would have to rotate this front carbon in the Newman projection and bring the R2 over to the side with the methyl group. So I've done that. I've brought the R2 over to the side with the methyl group so that we could have a R2 and the methyl group on the same side and the R1 on the same side as the hydrogen. That rotates this proton that's getting removed to be on the same side as the leaving group, which is not the anti-arrangement that we need for an E2 reaction. So that's why this one does not form. So it's not always convenient to be drawing a lot of Newman projections when you're trying to do the problem. If you want to, you certainly can. But another way to look at this is to look at the stereochemistry of the halide. This one that's leaving is above this drawing. It's sticking out at us, so it's above this drawing. So the hydrogen that has to be removed is going to be below the drawing. And in this case, the way that this is currently drawn with the zigzag, it does have the hydrogen in the right configuration. So we can draw a product that looks a lot like what we already have here on the paper. So we already have something with the ethyl group off to the right and the methyl group down. That is the one that has the hydrogen in the right position. So we could go ahead and draw the product that results from that. So this one tells us to use the benzylic hydrogen, not this hydrogen that is on the end. This benzylic hydrogen is going down away from us because the methyl group is coming up, and then this chlorine, or the chloride, the leaving group, is also going down. So these are on the same side. That is not going to work very well, but we do have a single bond that can rotate, so let's go ahead and do that. So I've rotated around this single bond over here. I'm going to rotate that until that methyl group is pointing down. And so that brings the hydrogen into the back, the chloride into the front. And so now we have the right configuration for the anti-elimination to take place. And that gives us the Z configuration rather than the E. So one thing we can do if you're not that good at rotating, either with a Newman projection or the way I've just done it, is just to know that the one that it looks like is on the paper here, the way that it's drawn, if you just remove the two groups and put a double bond there, you would get the E configuration. But since you know that that's not going to work because they're both facing the same direction, you can just go straight to drawing the opposite configuration to what you see there. Let's see if I could try this one as well. So here we have just one neighbor to pick on. This other neighbor does not have a hydrogen. The hydrogen that is on this neighbor is going back. We know that because the methyl group that's attached is coming up. It's drawn as a wedge. So we again have this problem where the hydrogen and bromine are not on the opposite sides like they should be. So if we draw it the way it looks here, so taking them both off of the same side would lead to this. That's not the one that's going to form because they're not on opposite sides. And so we can just go ahead and take this newly forming pi bond and draw it in the opposite way. So we could either switch this side and have this tert butyl group pointing up instead of down the way it was, or if we want to keep that, if we want to keep the tert butyl group in place, we can just switch the other two groups to get the other configuration. So we know that it's not E, so we can try to draw the Z configuration. These are both the same thing, they're just flipped depending on which side of the alkene you decided to swap. So this one is the one that would form. For cyclohexanes, we can't rotate the E and Z isomer of product that forms like we can with a straight chain. What we have to do is decide whether either neighbor can be picked on. So when you're looking at the carbon that has the leaving group, then the neighbor carbon that you want to pick on is one that can have the hydrogen on the opposite side of the ring. So if you have the hydrogen on the opposite side of the ring, then it can have a chair configuration where both of these are in axial positions on opposite side of the ring, and that is the configuration that will do the E2 reaction. So these have to be on the opposite sides of the ring to be able to do an E2 reaction. So let's take a look at these examples. We want to give the major product formed, and so we do want to form the more substituted alkene if we can, but if we are doing an E2 elimination, that has to be eliminated in an anti-periplanar configuration like we mentioned, and so if they are not on opposite sides, we can't do the E2 elimination. We might have to choose a different neighbor. So let's take a look at this first one. We have a bromine that is sticking up. We have two possible neighbors to pick on. We would like to pick on this more substituted neighbor. However, we need to have the hydrogen on the opposite side of the ring. So let's draw in our hydrogens that our neighbor has. This neighbor has a hydrogen pointing up because the methyl group is pointing down. This neighbor has a hydrogen pointing up and a hydrogen pointing down because they are both hydrogen on this guy. So we're going to have to lose the bromide that is pointing up and the hydrogen that is pointing down. So out of the three hydrogens that are around it, we need to lose this one. And that's going to form the less substituted alkene product, but that is the only one that can be formed by an E2 mechanism. And that is what it looks like there. I haven't drawn the other hydrogens in, but you can if you want to. So here we have a carbon that has a chlorine on it, and we have a couple neighbors to pick on. Let's draw where the hydrogens are. This neighbor has a hydrogen pointing down. This neighbor has a hydrogen pointing up. Since we are losing the chloride from the bottom face of the ring, we need to lose a hydrogen from the top face of the ring, and that is going to result in this product here. For this particular case, either product formed would have been tri-substituted, but again, the geometry of the E2 elimination makes this product the more favored product that can form. Here we have an extra tricky case. We have a bromine on top of the ring. Both of the neighbors have hydrogens that are pointing up, also on top of the ring. I guess both of the most obvious neighbors, I should say, that would put the cyclohexene together, or would put the alkene inside the cyclohexane ring. But there is a third neighbor here with a bond that can rotate freely because it's not part of the ring, and so this particular one can rotate so that one of the hydrogens is pointing opposite to the bromine. So we can have a base come in and take a hydrogen that's pointing down, get the bromine that's pointing up to leave. This is maybe the less obvious product here, but this would allow for an anti-elimination that we need for the E2 reaction. So another type of elimination that you can have is an E1. This is similar to the SN1 in that the halogen, the halide, reacts by itself. It does not have the base attack it during the rate limiting step. The leaving group leaves on its own, forming a carbocation. So we need a cation that is somewhat stable to be able to form. So tertiary is good. Here we have a secondary allylic one. So that can also form pretty easily. The problem says to draw the transition state, so we'll go ahead and do that. So the only thing happening during this transition state is this bond to the leaving group is breaking. There's a developing positive charge on the carbon, a developing negative charge on the halide. Then we have the carbocation intermediate. So the next transition state looks like this because the base is starting to come in and get the proton, and instead of being a full positive charge on the carbon, this is just partial because the electrons from this hydrogen carbon bond are starting to become a carbon-carbon bond. The base, I drew a delta negative. This does not have to be a very good base. It does not have to be a very strong nucleophile or a good base, because this double bond really wants to form, and so this proton is a lot easier to pull off than it normally would be for a carbon-hydrogen bond, because that allows for the positive charge to go away. The product is not a cation, so the product is way more stable. So it's a lot easier to pull off this hydrogen than you might think. So this can happen with even a neutral, not charged base here. The things we were talking about just a few minutes ago about the type of product that would form, would it be monosubstituted, disubstituted, EZ configuration, that all still applies. You would get the more substituted, more stable product, whichever that would be for your halide. All right, so for the E1 reaction, remember that you have to have the halogen leave first. So this one would be a very good candidate, this tertiary one. This one is a little bit tricky, these two over here. Comparing them, when the chloride leaves, you would form a benzylic cation, which is fairly stabilized. It's not that hard to form, but this particular compound does not have a neighbor that could form an alkene with it. So this is not going to undergo an elimination reaction. If the cation forms, we're going to have a nucleophile come in and do an SN1. So this would be able to undergo an E1 reaction fairly easily though. This one over here would form a cation that is allylic, so that is pretty stable. That would be able to leave on its own fairly readily. These ones, remember, vinyl and aryl halogens cannot do SN1 or SN2 or E1 or E2. These are not going to leave very easily on their own. So these are definitely no on these guys. And definitely no on this guy, because there's no way to do an elimination. These ones, there's possible they would not react as easily as the ones with the circles, but I'll go ahead and underline them, because secondary can still do E1, especially if you have conditions that favor elimination, like heat, protic solvents. So those could undergo E1. The ones that are circled will be the best candidate. So the major product of the E1 reaction, we can think about it in a similar way to the E2 reaction. We're going to form this cation first. So the bromide leaves, forming the cation, and we have three different neighbors to pick on. We're going to pick on that more substituted neighbor so that we can have that more substituted alkene product. So the E1 is a lot of times favored by a more neutral, milder base. So this is hardly even a base, it's very mild. It does have some a lone pair that can accept a proton. If this were a negatively charged one, if this were a stronger base, then you would probably get the same product, but it would go maybe through a more concerted E2 mechanism, because the base would be stronger. It would be grabbing the proton as the leaving group is leaving. Here we have a very mild base, so the leaving group can leave first. But we do get the same product for this one. We have a similar thing here, a very mild base that's letting the leaving group leave first. We have a few different neighbors to pick on. The most substituted neighbor will give us the most substituted alkene product. So that is the major one that is going to form. This next problem introduces the idea of allylic cations forming. So in an E1 reaction, the bromide would leave on its own, and then we would have a cation that is delocalized over two different carbons. And it's just good to be aware of this possibility, because since the carbocation is now in two places, we could remove a proton from this neighbor and get the alkene to be here. I'll go ahead and draw that here next to this cation. So this resonance structure makes it clear that you could get this as a product. Here you could pick on this neighbor. So this resonance structure leads to perhaps unexpected product if you're just looking at the starting material and not thinking about the delocalized cation. So we can get these two different regioisomer products here. We'll do the same thing with this halide. When the leaving group falls off, we have an allylic cation. So I'm drawing just the E configuration of these pi bonds, just focusing on the regiochemistry here. We could have the positive charge on the carbon that used to have the bromine, or we could have the positive charge 2 carbons over. So this top carbocation that I've drawn can lead to this isomer of the product. The bottom one can lead to this other isomer, like maybe the less obvious product that can form from this. But it's just good to be aware that with allylic cations, you might be able to get more than one possible product. So this is one thing that is different for an E1 versus an E2. This second product over here would not be forming very easily with an E2, because with an E2 you would have a base that is coming in and taking off this hydrogen at the same time that the bromine is leaving. So the E2 would only form this top product over here. The E1 can form a mixture of products more easily. So what is some other evidence that we even have this E1 mechanism that is possible? And that is called the deuterium isotope effect. So this deuterium isotope effect comes into play because deuterium is heavier than hydrogen. Deuterium is the isotope of hydrogen that has a mass of 2. There's 1 neutron and 1 proton in the nucleus, whereas most hydrogen only has the 1 proton in the nucleus, and so it has a mass of just 1. Both of them have the atomic number 1, but there's a difference in the mass because the deuterium has that neutron in the nucleus that gives it double the mass that a hydrogen atom, that a quote-unquote normal hydrogen atom has. And so the deuterium is heavier. Also, the bond between carbon and deuterium is stronger than the bond between carbon and hydrogen. And so if you have to break a carbon-hydrogen bond in a rate-limiting step, you can test that out. You can experiment by replacing the hydrogen with deuterium and seeing if the reaction goes more slowly. And so you can, people who are trying to figure out mechanisms can use this to see whether a hydrogen bond breaking is part of the rate-limiting step. So let's take a look at our reaction mechanisms and see where we would notice this deuterium isotope effect. So for SN1, the first step is a leaving group leaving. So we have a couple of different reactions where a carbon halide bond breaking is the first step. SN1 falls into this category, E1 falls into this category, so neither of those would have the deuterium isotope effect. For SN2, this involves a nucleophile coming in and attacking a carbon and pushing off a leaving group. So there's no carbon-hydrogen involved. There's no carbon-hydrogen bond involved in that rate-limiting step either. So the E2 reaction is the one where you have a base coming in and grabbing this proton and breaking this proton-carbon bond, this hydrogen-carbon bond, in order to form a pi bond and kick out the leaving group. I didn't give myself enough room to draw the leaving group on the opposite side like we learned for E2, so I'll try to fix that. But this is the one where we're having a carbon-hydrogen bond breaking as part of this only step. The rate limiting step is the only step in the mechanism. So this E2 is the one that would show a slowdown if we replace that hydrogen with a deuterium.